Okay, so we're going to go into modeling with variation. So we just re-looked at applications with rational expressions, and this kind of ties into the applications portion of that. Then how to look at a verbal description and identify what type of variation it is, whether it's direct, inverse, or joint. And then isolate and interpret the variables within that. So direct variation is what you learn kind of straight out of the gate. It'd be something like y equals k times x, where you have this constant k in your problem. You are multiplying one time. Somewhere within that problem. Notice you don't have like a y-intercept or a constant being added to that. Inverse variation, we're going to invert that. So we're going to flip this essentially on its head. And remember, you find an inverse, you flip the x and the y and then solve for y. So we have k over x, this k still being the same k as above. And so we're dividing once. And you may need to review your notes on inverses for this if you'd like. The joint variation, we're going to kind of combine those two ideas. So you have y equals k x times z, where you still have your k, but you are going to multiply twice. In all situations, this k is what we call the constant of proportionality. And it will be a part of every question that you do that has to do with variation. And it's a constant, so you can use it then to find or project values that will be coming in the future. So it's much like your slope. And in fact, in direct variation, it is the slope of that line. Okay. So steps for modeling, you're going to write the model for the problem using variation principles and appropriate variables. Find the constant of proportionality, so essentially solve for k or solve for x. And then rewrite the model with the value of the constant so that you have an equation. Use the model to answer any questions posed in the problem. Again, we can use that constant to project or solve for future values. Okay, so all of that was a bunch of gibberish, I'm sure. So let's look at an actual problem and see what we're dealing with here. So the distance a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. During the first second, the ball rolls 8 feet. How far will the ball roll the first 3 seconds? And so a couple key things here. The first thing we're talking about is the distance the ball rolls, right? So we know that distance is equal to rate times time. And so that's where this comes in. The fact that we're multiplying once gives that to us. And this tells us it is directly proportional. So we're using that idea of, again, multiplying once by something when it's directly proportional. So then we can use that kind of formula to write our equation. So our distance is going to equal your constant, your constant of proportionality times, and then it says right here, the square of the time, the square of the time. So distance is rate times time, but when we write in our y equals kx time is our x, but we need to square that. So we need to square our x value. So we have t squared here. Okay, so again, our k is our constant proportionality. This is what we need to find. And so this is part A, where we just write our equation. Okay, so write a model for the problem. This is our model. We can then solve for k by plugging in things that we know. So we know during the first second, the ball rolls 8 feet. So we can plug all that in. T equals 1, and the distance was equal to 8. All right, so 8 is equal to k times 1 squared. Well, 1 squared is 1. Divide that over. K will be equal to 8. This is true continuously. All right, so then we can go in and say, okay, well then how far does the ball roll during the first 3 seconds? So part C, we know that time is 3. We want to know the distance. And so we're going to now plug in everything else that we know. Well, we know, or sorry, part C says to rewrite the model. So part C is saying that the equation for this function, and what you would graph in like a graphing calculator, would be d is equal to 8t squared. And so then we can use that, knowing that our time is 3 and we don't know d, we can plug in. So d is equal to 8 times 3 squared. Okay. So we square our 3 is 9 times 8. Our distance then would be 72 feet. So what that means is that the ball can't spell here, rolls 72 feet in 3 seconds. All right, so let's look at another example of inverse variation. And so it says here, the number n of square tiles needed to tile the floor is inversely proportional to the square of the length s of a side of each of the tiles. Okay, it takes 180 tiles with 6-inch sides to tile the floor. And then we want to know from that, how many tiles with 9-inch sides will it take to tile the same floor? Okay, so we have n is the lengths of the sides of each tiles, and n is the number of square tiles needed. Okay, so if we're writing a model for this, we're using inverse variation. So y is equal to k over x. Okay, because it's inversely proportional. So n, the number of tiles needed on the floor, is inversely proportional. So n is equal to your constant divided by your s squared, the square of the length. Okay, so inversely proportional. What is inversely proportional? N is inversely proportional to s squared. Okay, so that's how you need to think of it. All right, so we're going to plug in what we know and solve for B. It takes 180 of the 6-inch side tiles, so 180 for number K, and then 6-inch side tiles to tile the floor. This is 36, so we're going to multiply both sides of this equation by 36. And we get that K is equal to then 6,480. And this is talking about a square feet. Okay. So our equation is that n is equal to, and we plug in our constant of proportionality, 6,480 divided by s squared. All right, well, that makes sense. When I take S squared, I have the square feet for each tile. And then when I divide that by 6,480, which is the total square feet, I will have how many total tiles I should get. So make sure your answers are making sense as you go. I want to know how many 9-inch side tiles do I need. So I'm just going to plug that then in for S. So N is 6480 divided by 9 squared, which is 81. Just type that in your calculator and you'll get that N is equal to 80. And then that's how many tiles you need. Okay, so we can conclude we need 80 9-inch tiles to cover the floor. All right. Okay, so let's look at a joint variation problem. And so again, this problem will say something about varies jointly within the problem itself. So the cost of constructing a 9-foot by 12-foot patio is $734. The cost varies jointly as the length and width. So hopefully you can see here we have length and width and something varying jointly to that. So we're multiplying length times width. We're multiplying twice, okay? And so varies cost, length, and width. You have 3 things there. So we have joint variation, which is y equals k times x times z. And in this particular case, you have the cost, which is varying to the length times the width. Okay, so we're taking our constant of proportionality times the length times the width. And so we have our 3 variables there. All right. We know that the cost of constructing a 9 by 12, so there's our length and our width, 9 by 12, is $734.40. And I didn't leave myself enough room here. All right, so if I solve that for K, and I'm just going to start over. Okay, so we know that so far, and I haven't even finished reading the problem yet, but we know that C is 734.40 when L is 9 and W is 12. And it doesn't really matter which one you put as length and width because we're multiplying. So we can plug that into our equation. 734.40 is equal to K times 9 times 12. And then we can solve this out. All right, so divide both sides by 108, which is that product of 9 and 12. So K equals 680. What does your constant of proportionality represent? Okay, this is your cost per square foot to install. Okay, so our equation then is the total cost is equal to our cost per square foot times the length times the width, which makes sense because length times width is area, and then our cost per square foot would give us the total amount. All right. I want to know in part D, what does an 8-foot by 14-foot patio cost? And so I'm just going to plug those in. C equals 6.8 times 8 times 14, and type that in my calculator. I get 761.6. So the cost of an 8 by 14-foot patio is $761.60. Okay, so now you've seen all 3 types of variation. We're going to do one more because you can combine your types of variation. And so I just want to show you what that looks like. Okay, so the time T required to process the shipment of oysters varies directly, and so we have a direct variation here with the number of pounds P. And so if we're looking at this in terms of direct variation, we have y equals k times x, where your T is essentially, your T is what we're solving for. So T is equal to K times P, what it varies directly to. So that's what we have so far. So I look like a minus sign. All right. And inversely with the number of workers, W. Okay, so if this were an inverse variation, it would look like this. Okay, so remember your constant of proportionality is the same value all the way through a problem. And so all we're going to do here then is if it's inversely related to W, we're going to put the W on the bottom. So as soon as you divide by a variable, you've made it an inverse. Okay. Up here at the top, this is direct. Okay, so you have your direct variable and your inverse variable. K is the same throughout. Okay, so that's the biggest difference with this one. All right, we're still going to solve it the same way. So it says if 300,000 or 3,000 pounds can be processed by 6 workers. Okay, so pounds, workers in 8 hours time. Then how long would it take 5 workers? And we don't need to answer that question yet. So we have time, it says 8 hours. Workers, it says we have 6. Pounds, it says we have 3,000. Okay, so 8 hours for our constant of proportionality times how many pounds we have divided by how many workers we have. And then we solve this out. So we get 8 equals K times 500. So K is equal to 8 over 500, which is like 2 over 125, or 0.016. Okay, so either of these is fine. Then we want to know how long would it take 5 workers to process $4,000. So I want you to go ahead and try this problem. Write your, now using your K, go back, write your equation, and then plug in and solve. Okay, so here, rewrite your equation that we started with plugging in your K. Then it asks us for 5 workers, 44,000 pounds. So I plug in P and W and solve for 12.8 hours. If this asks for hours and minutes, then you're going to take your 0.8 hours, multiply it by 60, and that actually gives you 48. And so 0.8 hours is the same as 48 minutes. So then we can conclude that it's going to take 5 workers, 12 hours and 48 minutes to process 4,000 pounds of food. All right? And that's it for variation. I know this is a weird unit to stick it in, but if you have any questions, let me know.